This is the introduction video for inverses and log functions. Our learning outcomes are to determine if functions are inverses of each other, find inverses of relations or points, inverses of equations, and inverses of graphs. And then we also want to make sure we introduce and graph log functions, which are the inverse of exponential functions. One of the things that will help us determine if two functions are inverses of each other is to see about their compositions. We learned about compositions of functions in our first unit, in which we found f of g of x. And we found that not all the time did we ever find g of f of x to equal to the same thing as f of g of x. If they do equal to each other, and they will equal to each other only if they both equal to x. In other words, g of x does something to the x and the f undoes it. And the same thing happens over here. So when we find that f of g of x and g of f of x both equal to x, then the function g of x is said to be the inverse function of f of x. And this is how we would write that. Likewise, we could say this the opposite, that f of x is the inverse function of g of x. So either one will do that. So I just wanted to make sure that we can do it by using composition. So I want to refresh your memory about how to do that. So let's see if we can try an example. So let's say we have these two functions and we want to find f of g of x. Let me just remind you that means we're going to get x. We're going to plug it into our g function. Whatever comes out, we're going to plug it into our f function, and whatever comes out is our result. So this is our g and this is our f. So our g function says I take the square root of whatever you give me minus 1. So if I plug in x here, I'm going to get the square root of x minus 1. The f function says I square whatever you give me and add 1. So if I square my square root, we've realized that that's just going to be x minus 1 plus the 1. We're going to see that that equals to x. Now, just because we solved this one is equal to x, doesn't mean we can't do the other one. We have to do the other one. In other words, we have to find g of f of x, which means we're going to plug in x into my f function. Whatever we get, we're going to plug it into our g function, and then whatever we get, we hope it's an x. So let's see if that's the case. So I plug in x into my f function that says whatever you give me, I square and add 1. That's going to be x squared plus 1. My g function says whatever you give me, I'm going to subtract 1 and then take the square root. So I'm going to get my x squared plus 1 minus my 1 and then take the square root. So we can see that the 1 and then minus 1 will go away, and the square root of x squared is x. So it does work, and we find that these two functions are inverses of each other. Another skill that you're going to find useful is to be able to solve for the letter y. So if I have x is equal to 2y plus 5, and I say for you to solve for y, don't forget we are going to subtract 5 to both sides. That's going to give me my 2y. And then I'm going to divide everybody by 2, and I mean every term by 2. So we're going to have x over 2 minus 5 over 2 is equal to y. Now don't forget, because we have the same denominator, we can just put our numerators together and have it as one fraction. Either one will work, so I just wanted to make sure you remembered how to solve for y. And we're going to do it again with a little bit more complicated problem. So here we have x is equal to y squared plus 2. So again, we're going to solve for y, so I'm going to subtract 2 to both sides. So I get x minus 2 is equal to y squared. And then I'm going to take the square root of both sides, and I'm going to have square root of x minus 2. Now, I do want to make a little comment about taking square root. So normally when you take the square root, you need to make sure you add plus or minus. If the equation says that they're taking the square root, then they're always taking the principal square root, which is positive. So if it's given, it's automatically positive unless there's a minus sign on the outside. But if you have to go write down the square root, don't forget the plus or minus. So we'll talk a little bit more about that as we go along in the video. So let's go to the first learning outcome that asks us to determine if functions are inverses of each other. So we kind of did one where we said that we can see if functions undo each other, and we did that with our compositions. So we can see that that information is right here. Another way that you can see if a function even has an inverse is to see if a function is one-to-one. For a function to be one-to-one, it needs to pass the horizontal line test. And if it does, then it does have an inverse function. So we can go take a look at our parent functions and see which ones pass the horizontal line test. So here are our parent functions from unit number 2, and let's see which ones pass the horizontal line test. Just to remind you, the vertical line test tells us if our function is a function, if our graph is a function. The horizontal line test works the same way, except it's going to tell us if it's one-to-one. And if it is one-to-one, then we can find an inverse function. So if we look at our constant function, I'm going to draw a horizontal line, and we can see that it does not cross one point, but infinite many. So this one is not one-to-one. So I'm just going to write it out here. Not one-to-one. If we look at linear, and if I draw a horizontal line, we can see that we're always cutting into one point at a time. So this one is one-to-one. At absolute value, we can see that it actually hits 2 points, so therefore it is not one-to-one, which means when we find the inverse of a absolute value function, it's not going to be a function, if we can even find the inverse at all. Quadratic has the same problem that we have with our absolute value, that we actually get 2 parts. So the way it's written like this, it is not one-to-one. But what we're going to find out is that if we had our quadratic function like this, and we restricted the domain so that we only looked at half of it, then we're going to see that it now passes the horizontal line test, and this is one-to-one. But again, remember we had to restrict our domain. So our domain could not be from negative infinity to positive infinity in order for it to be one-to-one. So we could do the same thing with the absolute value if we had to. Let's go to square root. We can see if we do a horizontal line test, we're always getting 1 point. So this is one-to-one. Cubic is one-to-one. Cube root is also one-to-one, so we can see that here. Reciprocal is also one-to-one. I know it looks like it has more than 1 point here, but remember it's always decreasing, so therefore it has to be one-to-one. Now the reciprocal squared, we can see right here it does not cross the that it does cross the horizontal line twice, so it does not pass the horizontal line test, so this one is not one-to-one. Logarithmic is one-to-one. And exponential that we see right here is also one-to-one. And if we look at our sign graph, we can clearly see it is not one-to-one. So a quick way to decide if a function has an inverse function is to see if it is one-to-one. And we do that by applying the horizontal line test. So now let's go to our second learning outcome that says find inverses of points, equations, and graphs. So one of the things that we're going to find out to find the inverses of points is that if you have a point A, comma B, its inverse is B, comma A. So if I had the point 2, comma 3 and another point 5, comma negative 1, then we can find the inverse. If this is function, the inverse function would be the set of 3, 2 and -1, 5. Another way to find out if these are one-to-one is just to graph these points. So I would go to 2, 3, and then I would go to 5 and -1, and we can see that it does pass the horizontal line test, and they are functions because it passes the vertical line test as well. If we're given equations, we can actually find the inverses by switching the x and y's. So if we had y is equal to 2/3 x plus 5, and we want to find the inverse, then I'm going to switch the x's with the y, so this would be 2/3 y plus 5. So I just switched them, and now we have to solve for y. So I'm going to subtract 5, so I'm going to have x minus 5 is equal to 2/3 y. Then I'm going to multiply by 3/2 to both sides. 3/2 x, and then I'm going to multiply 3/2 times my 5, so I'm going to get -15/2 is equal to, and I multiply by 3/2 is equal to y. So if this is my function, then this is my inverse function. So now you see why we reviewed how to solve for the letter y. And finally, if you're given a graph and you need to find the inverse graph, remember that the graphs are going to be reflected about the y is equal to x line. So we're going to show you a quick example about that too. But another easy way is to pick up some of your points of your f of x and graph the inverse points of your f of x, which we discussed at the very beginning of this learning objective. Here's my note about my x squared need to have the restricted domain in order for us to find the inverse function. And then we'll also talk a little bit in just a second about finding the inverse of y is equal to 2 to the x. But first I wanted to look at some graphs. Here's the first one I want to show you. So we're given that our equation is y is equal to 2x plus 3. And they graphed it for us, and we see that our y is equal to x, and this red one is our inverse function. So again, remember we switch the x's and the y's, and then we solve for y. So this equation is going to be the same thing as this equation here. So I just wanted you to see what they look like in terms of graphs. Here are a couple more that are inverses of each other. We can see the red one. Notice I said that another thing you could do is pick some points of your graph and then switch them around, and then you'll get your inverse graph. Same thing is happening over here. We're going to come back to this graph in just a second. And over here we can see that if this is our y is equal to x squared, the inverse would be this red one, but it will not be a function. So in order to make it a function, we would have to restrict the domain to either be just this side, so that way my inverse would be just this top part, or we can just select this side, then the inverse of it will be just this part right here. So it depends on which part of the domain you restrict. And then finally, we'll go back to this last graph over here. And what we find is that if this function right here was 2 to the x, then this function over here is a log of base 2 to the x. So what we find out is that when we're trying to find the inverse of 2 to the x, we actually have to introduce a new function. So let's do that. So here we were trying to do it for graphs. I showed you a few graphs. And then the last thing I said was to go find the inverse of y is equal to 2 to the x. And we realized that if we had y is equal to 2 to the x, and we switched our x's and our y's, that we would still have a hard time trying to get y by itself. We can't take the square root, we can't divide by 2, so we actually have to introduce a new function called the log function. So let's see. So you've just discovered the relationship between the exponent and the log functions. They are inverses of each other. So what we want to get out of this is that if you have the base to some exponent is equal to some answer, and you're trying to solve for the exponent, that you can find that the log of the base of the answer is actually equal to the exponent. So that's one way we can solve for the exponent. And then we can also, so I wanted to make sure that you remember this translation between bases and logs. So if we had 2 to the third is equal to 8, then I can also write this as the log of base 2 of 8 is equal to 3. So a lot of students say this relationship, that 2 to the third power is equal to 8. So that's one way of remembering it as well. And then last but not least, I want to remind you a little bit about transformations. We have a log parent function, so let's talk a little bit about that. So for us, in our parent functions, we have y is equal to the log of x. That's what we call a common log because the base is 10. And what that means is that we have a point here at 1, there at 0, 1, 0, and our graph looks like this, going down to infinity and slowly coming up this way. Which means that if I go all the way over here to 10, this number right here is going to be 1. So that's what it means in terms of base 10. So the other thing I want you to realize is that we actually use the log base to do earthquakes. So if you hear an earthquake has a Richter scale of 5 and another earthquake has a Richter scale of 6, it just means, oh, there's a difference between 1, but it actually means that it's 10 times stronger because we're using base 10. But that's a side note. But what I want to make sure that you know is that we can apply our transformations with logs, that if we have x plus 2, we still need to know that it moves it 2 units to the left. So this point would be over here at 2 units to the left. And it would still have the same shape. Again, if we have log of base x plus 2 like this, usually you'll probably see a parentheses like that, so you know that this means we're going to shift it up 2. So this point will actually be up here and then looking down like that. So I just want to remind you of what you already know in terms of transformations of log functions. And that concludes this video.